16.3, 16.4. So this is hash code and hash tables. We're not going to get too much into how the hash table actually works. You just need to be able to compute the numbers and know how, just have a basic understanding of how it works. So a really fast way of finding something is if I could turn everything into an integer number and then store that in some sort of array. Remember, accessing any element in an array is O of 1, right? Because I just go look at the number, it's one step, it's great. The trick then is converting things that aren't actually numbers into numbers. So we have what's called a hash function, which is some function that is able to convert things for object, so it changes some object into an integer value. Okay, so just some randomization, some number representation. The object class does know how to do it. I could have some object x. I could do int h equals x dot hashcode is the command, which is the built-in hashcode generator, which would then turn x, create an integer number h, which represents x in some form. Alright, so table 1, page 708 says if you were to type in these strings and get the hash code of them, the computer will generate the following numbers. Now, obviously, it's impossible to have a unique number for everything, otherwise our storage array for searching would be too large. So what you do have is you do have the chance of what's called a collision. That's where two objects have the same code, or the same hash number, which is obviously a problem. I can't store two things in the same array or I can't get it back. So a good hash function function minimizes the collisions, so I don't have as many. Now, if my most basic level, I could generate numbers. As long as they're all positive, I could just put them into an array, and then the index for the array would be the number that is generated by the hash function, but that's just impractical. It's too large because you're not sure what number is going to be generated. So what you're actually going to do is shorten it up. So for some value h off of the hash code method of the object class, then I'm going to check if my h value is negative, which doesn't do me much good, then just transpose it, give me a positive value, and then chop it up, make it smaller. Some number, something called size. Okay, so take the remainder of my integer h divided by my size value. And it's recommended that size be an odd number, and generally fairly large. We're not going to deal with anything too huge, but you want to be able to minimize things. Now, once you minimize this, your chance of collisions goes up, because then we're sort of reducing every number because we can get the same remainder off of a bunch of different numbers. So what we're going to do is we're going to create an array. Okay, but instead of being an array that fills up with integers, each index is going to be a node, and I can then have what we call buckets of nodes, just like a linked list. We're going to make mini linked lists for each array index. So anything that has the same collision or the same hash code because of a collision, we'll put in the same spot, but there'll be, one of them will be here, and then one of them will be off as the next node. So I can put a couple things essentially in the same spot. So the algorithm for finding an object in a hash table, once we put it in there, you're going to compute the hash code, reduce it to modulo the table size. This gives my index h, so here would be the table size that we're generating to store everything. Iterate through the elements of the position of the bucket at position h. For each element of the bucket, check whether it's equal to my object. If I found among my elements, then x is in the set, otherwise it's not. So if this was hash number 65, I would go through and let's say these are names, Dave and Bobby, and I was looking for Bobby. First you would call this on the hash code on Bobby, divide it by your size, the remainder would be 65, and you'd come through and then you'd iterate through. First one is Dave, it's not there. Next one's Bobby, boom, I found it. So in this case, this would be 5 steps. So a fixed size, so O of 1, essentially, because constants don't really count. Doesn't matter how big my array got, it still wouldn't take any longer to find Bobby. Yep. So 2 things. If there are no or only a few collisions, then adding, locating, and removing is a constant time, or O of 1. And the table size should be a prime number larger than the expected number of elements. Usually I recommend some excess, about 30% of the number you expect to be storing, just to give yourself room. So page 710 has the hashset.java file. We're not going to really go through it too much, but you can look over it on your own. It's pretty straightforward to make a bucket. And I have my size of my array, that's my parameter. I have a method contains, which checks whether something's in there. I have a method called add, which just adds it to a bucket as appropriate. I have a method remove. I have an iterator that walks through everything. And I have in a node array of buckets. I have an integer of sizes. And then I have my internal private class node, which is just like the one for a linked list. And then I have an iterator to actually go through the bucket for me. So that is 16.3. That's sort of the generics of hash code. So 16.4 is how would you actually go about computing it. So we know that I can use the built-in object hashcode method for anything. It's an object. But what if we wanted to make our own? So on page 715 you can see the method that the computer, your standard library, actually uses. And it is the following. I got final int hash multiplier equals 31. Oh, sorry, that's a bad 31. Int h equals 0, and int I equals 0. I is less than s dot length. I plus plus. This is for strings. H equals So doing it this way, so I get the multiplier times my value, and I add my character into it, because each one of those has its own unique number. For instance, eat would come out to be, the file would be 100,184, whereas t would be 114,704. Because I would want those to be different, even though they have the same letters. They are different orders, therefore they should generate different codes. So it's 31 times E plus A plus T, which is very different from 31 times T plus E plus the A. So we use the Unicode table. In the back of the book, it's Appendix B, look up the values. So the value for A would be 97, E is 101, and T is 116. So the order in which you do these does matter. Okay. Now what if I was doing something like a coin class? Well, I could just use the value, but I really should compare both. Okay. So you're going to always want to combine. I mean, because if I had a coin class, dime equals new coin. The problem is if I just, I already have a number, that's great. But the problem with just using a number is something else could obviously have that value. So what I want to do is I want to combine all instance fields. Okay, so I'm going to combine all the instance fields, the hash code for those, into hopefully what is then a unique one, or at least one that minimizes potential collisions. So coin has both a name, which is a string, and a value. So you would want to combine the two. And then I just get to use that number that I generate. That'll be hopefully unique enough for each coin. Your hash code method must be compatible with the equals method, so that if I generate two objects, I should have the same hash code for them always. So one note, obviously we have our way of doing it for a string, but for instance this does have a number instance field, so you just want to use that. If one of your instance fields is an integer, just use that and add it into the object or strings or whatever the other one is. Okay, so remember, two of them need to be two. So if I had 2 dimes, they should generate the exact same hash code. If I had a quarter and a dime, then I should get different ones, because I should generate hash code based not only on the value but also on the string name instance field. So if I was to look at page 717, the coin class, and adding the ability to compute hash code. So I already have my previous coin constructor, get value, get name equals. So in this case coin, so I use my equal method. And then I have my int hash code. So my first number is the get the name hash code, so that's a string, so I just call it. And then h2 is I'm going to use a double hash code, because it's technically, for instance, if my double field, well, that's a primitive double type. That's not an object, so that doesn't have hash code. So I cast it into the double class, and then I can use that class's hash code. Have some multiplier, prime number, and what I'm going to do is I'm going to multiply my hash multiplier times, I'm going to add the first two together and multiply them, and I'm going to return that value. So that'll hopefully give me a unique hash code based off both the name and, in this case, the number that I have, and then return that for use.